Welcome to our first CCOM seminar for the year. My name is Kelly Nifong. If you don't know me, Scott Loringer is the other coordinator this year. He's currently getting married this weekend, so that's why he's not here. Dr. Jamie Pringle is going to introduce our first speaker.
I've now known Miles since 1992, which is a long time ago now. Is that 22 years? Mm-hmm. So we went to grad school at the joint program where he studied turbulence and dispersion in complicated and simple numerical models. He then went on to do a postdoc at UMass Dartmouth back when it was CMass. It then turned into SMass, the School for Marine Sciences and Technology, if I'm remembering correctly. And Miles has continued to look at how to figure out what mixes stuff in the water. And recently he's been focusing on the mechanics of doing that, which are very, very difficult, because you need to capture lots of different degrees of freedom so you can average enough to tell anything. So, that'll do.
Thank you, Jamie. So thank you for coming. What I want to talk about is specifically a field experiment we did in 2011. I study ocean mixing, so I'm trying to understand the physics of what drives ocean mixing from scales from meters, tens of meters, up to, it could be basin scale, hundreds of kilometers, mesoscale eddies. I'm interested in fundamentally what are the physical processes, and hence how do we parameterize the mixing and predict them in unknown environments. So I'm going to talk about some observations of small scale, what we call submesoscale lateral dispersion in the ocean, in the pycnocline. And then I also want to take the opportunity to introduce a new effort we have going in the UMass system. We're just starting up a center for experimental environmental Lidar, nicknamed Excel. And so I just want to introduce that, and just at the end I'll have a few slides of what the thrust areas of that center are. And that's really what spurred my visit here, talking to various people up here in CCOM and seeing what collaborations we might have. So this work is in collaboration with my former postdoc Daniel Birch, and I understand his father works here at UNH. And a couple of collaborators, Jim Ledwell and Gene Jere at Woods Hole Oceanographic, and Brian Kincannon at NavAir in Pax River is the operator of the Lidar and was a collaborator on this. So just to give a broad introduction of the type of processes I study. Mixing in the ocean, so I focus on lateral mixing primarily. I don't do three-dimensional turbulence. Lateral mixing where stratification starts to become important, and it starts, basically, it inhibits the vertical mixing, but the horizontal mixing, it takes no work to displace a fluid parcel on an isopycnal, and the horizontal mixing then is potentially controlled by much different processes than the vertical mixing that requires work to exchange a heavy and a light water parcel. And there's a whole slew of different processes, and this is my one slide of what I call the zoo of mixing processes, and I just want to give you a flavor of the extent of the different kinds of processes at different scales. And so really a canonical one that's been around for many decades, actually dating back to some work by G.I. Taylor in the 50s of shear dispersion. The idea that if you have a shear in the water column, so typically people, and Young et al. Talked about internal wave shear dispersion. If you have a stratified water column and you have two parcels of fluid, and that water column has a shear in it such that you displace those parcels of fluid. If you then also have diapycnal mixing that mixes water from here down or water from here up, then even if that's, let's say, a tidal oscillatory current that replaces these on top of one another, once you've mixed down, you've rectified the dispersion. So even if this parcel goes back, the dye that mixed, or the fluid that mixed, is now laterally spread on the same isopycnal as the original one. And so that's called shear dispersion. It's a rectified dispersion that happens between a shear and a diffusivity transverse to the direction of the shear. We think of it in typically, oceanography thinks of vertical shear dispersion, but you could have it in the horizontal as well. For example, if you have flow into an estuary and you have wake eddies that mix fluid across that flow, then by the time the water goes back out of the estuary, it's different water, right? Or vice versa going in. So that's shear dispersion. That's long been thought to be a controlling mechanism for horizontal mixing on scales of hundreds of meters to a few kilometers, open ocean as well as coastal ocean. You can also, from internal waves, the superposition of internal waves in nonlinear stratification or with nonlinear internal waves can also stir fluid. And again, that'll happen on the scale of the internal waves, which is meters up to kilometers. In areas where there are fronts, so here's an example of some numerical modeling studies. If you haven't seen, they're pretty compelling pictures when you see simulations of the instability of fronts in the ocean. And the instability that grows, and then you end up getting eddies associated. Baroclinic instability is a classic one, where you get eddies spontaneously generating from a mean flow. And those eddies mix fluid. They create boluses of water that transport water across the front. Right? Gulf Stream rings are a very extreme example of that, warm and cold core rings that transport boluses of water. So that's another mixing process that can happen on scales of kilometers for coastal fronts, up to hundreds of kilometers for mesoscale eddies like the Gulf Stream eddies. There's processes that the geostrophic flow in the ocean interior, basically the geostrophic flow, and so I'm referring to this work of Smith and Ferrari. The geostrophic flow in the ocean can also create shears, and the variability of the geostrophic flow effectively can create stirring on mesoscales. Here are some simulations that I was involved in a number of years ago where we're looking at mixed patches in the ocean creating small scale eddies. Basically, anytime turbulent mixing, three-dimensional mixing, is episodic in the ocean. And so if you have a patch of mixing in a stratified environment, you've now created a pressure gradient with the ambient environment, and there's going to be an adjustment. Really, like a small-scale geostrophic adjustment problem can happen, and you can spin up geostrophically balanced flows on scales as small as a few hundred meters. The associated deformation radius can be remarkably small. And those geostrophic motions, also referred to sometimes as a vortical mode, can cause stirring in the stratified interior, again, scales of hundreds of meters. So there's all these different processes, some driven by 3D mixing, some driven by internal waves, some by the mean flow. They can all contribute to mixing. The question is, when does which one dominate and how much mixing will it create? That's fundamentally what I study. So I want to get into how I study it, and I'm going to talk about an experiment we did in 2011 out in the Sargasso Sea. So here's Cape Hatteras up here. So we're a couple hundred kilometers off Cape Hatteras. We're in the deep ocean. We're on the ocean side of the Gulf Stream. So we're in just the very quiet Sargasso Sea mesoscale region. And I'll first talk about two rhodamine dye release experiments. Rhodamine is, if you don't know it, it's a fluorescent dye. You can measure it with a fluorometer. And we would put in 100 kilograms of rhodamine dye and then track it for 6 days with a ship. And so we would follow this dye around. And so here's the tracks and the evolution of what the dye did. So for scale, 5 kilometers in here is this little scale here. And so we're talking about the overall scale here is 25 kilometers or so. So what happened was we inject the dye down on an isopycnal and with a towed CTD and injector sled basically behind the ship. The dye streak when we put it in is about a 1.5 kilometers long. When you account for the turbulence behind the injection sled and a little bit of adjustment that happens as the weight collapses, we estimate probably about 100 meters wide is the initial condition. So 1.5 kilometers by 100 meters wide. And it's only about a meter thick in the vertical because we track isopycnals with our injection sled. And then we watch that advect and spread over 6 days, accomplishing about a survey a day, basically with the ship and a towed CTD and fluorometer package. So just to give you a better sense of the environment in the vertical, here's basically the profiles that came out of our surveys. And main features here is there's a mixed layer down to 15 or 20 meters, and there's a pycnocline, and it's stratified below that. And so we're down at 30-ish meters in the stratified region. So zooming in on these, so whoops, I went too far here. Okay, so this was one of the experiments. These blue and red and green lines are advection estimates from a Lagrangian flow from the ADCP from drifters we had in. And then this is roughly the magenta is where the dye patch went. And you see basically it went a little bit north first and then got advected southward, all the while starting to spread out. And I'll show zooms in of that. We did a second experiment in the same general region. It was a week later, and it was just maybe 50 kilometers north of here. And the second time we did it, we were in a saddle point of the mesoscale strain field. And what happened is then that dye patch advected northward about 200 kilometers. And while it went northward, it was getting strained and elongated so that by the time it went after 6 days, we estimated it was about 80 kilometers long, and it was just a few kilometers wide, so it's got stretched out. So let's go to some details of how we do our sampling of the dye. This is for the first experiment, the more quiescent one. And what I'm showing here is I keep hitting that one instead of that. Okay, what I'm showing here is the time after injection for the various surveys. These are all plan view. The black is the ship track. And on some of these, you can make out a dash gray ship track. What we do is we do our sampling in Earth coordinates, but if the water's moving along, we want an advected coordinate so we know if we're sampling the same water or different water. So what we do is the black is now in an advected coordinate reference frame, so that if on the black you see the track overlapping itself, we sampled the same water again. Otherwise, we're sampling different water. And so what you see basically is the evolution here. So for scale, down in the lower right, you can see what 5 kilometers is. So after 11 hours, again, this is a kilometer and a half long, and then we survey it, and you see the evolution. The red circles, the bigger the red circle, the more dye was found there. And you can basically see the shape of the patch. It's elongating, probably the easiest one to look at by the time it's 135 hours later. It's elongated to about 10 kilometers long. It's still about 5 kilometers wide, and you can see basically it's a fairly coherent patch, right? There's no blank spots in between. That suggests diffusive processes mixing it in. It's not that it's been sort of wrapped around and swirled around by 5 kilometer scale eddies. There's some small scale mixing process that has homogenized the patch and spread it out a bit. And if you go to the next one, this you can, after 10 hours, just to keep it on scale, I have to show after 10 hours, here's this tiny, tiny patch. This is already 5 kilometers long after 10 hours from the initial 1.5 kilometers. And you see by the time we get to 148 hours, we've stopped surveying the southern extent of the patch, so that's not in these last 2 panels, just because there's so much ocean we would have to cover to do an entire patch survey. But we're already, this vertical black line is 50 kilometers, so we're already at 50 kilometers after 100 hours, which means by 148 we're probably up to 80 kilometers with that. And so we're doing these Toyo surveys of the dye, where we have a CTD fluorometer, and it's yo-yoing up and down behind the ship. So we have each of these, any transect through the dye, we have the vertical section of the dye as well. And so what we do with this is our first order answer to what's the dispersion, how big is the dispersion. And so we take from a given survey, we can take all the profiles and basically put them in a density coordinate. That's the one that matters, how it mixes along an isopycnal, because isopycnals can heave up and down. We want to know mixing along an isopycnal, so in a density coordinate we can come up with a mean profile in the vertical for each survey, and then using a mean pressure density relation, we can map from the density coordinate back to a pressure coordinate, and we do that because diffusivity is in length per time squared. It's a length, it's not a density. So length squared, meters squared per second, right? We need meters squared, not density squared for that, for our equations of motion. So we get that in meters squared, and then we can basically, if you take each of these surveys, so this is from that first experiment, and you take a very simple diffusion equation, the vertical diffusivity is 1/2 the time rate of change of the second moment in the vertical. So that's the variance of a Gaussian profile. As that grows, that's the diffusivity by definition. And so these blue dots here are each of our estimates of the second moment in the vertical. And you see 2 curves on here, 2 straight line fits. Sorry. We see, I should just put this down. You see two straight line fits. The reason I have two there is these later surveys, again, we didn't finish mapping the patch. This is for the, did I say the first survey? This is the second experiment. I'm only showing the second experiment here. The late surveys in the second experiment, we didn't survey the entire patch, and so those are in dashed lines here. So these points don't fully represent the whole patch. So really, this magenta line is the better estimate of the vertical diffusivity. Because if you have a dye patch and it's getting stretched out like this, and this part, because of the stretching, the shallower part is here and the deeper part is here. If you only sample half the patch, you're going to bias your second moment small. You have to sample the whole patch to get this diffusivity estimate. So we can estimate a diffusivity. It's about 5 times 10 to the minus 6 meters squared per second, which is a fairly typical open ocean value. And in fact, that agrees pretty well with microstructure measurements and measurements from a Lagrangian float that were also out there at the time. So that's a diapycnal diffusivity estimate. And now, if you take this equation, which is the diffusivity as a second moment time, we're going to add a term to that. In fact, we're going to just not cancel out a term from the equations of motion. When we look at the horizontal moments, what we're looking at is the second moment of tracer changes in time. Here's that diffusivity. But in the horizontal, the second experiment is a really good example. It's straining as well. There's a strain field, which is an advected field, as well as the diffusive field. And so if we don't take that in account, we can't estimate the diffusivity. So gamma here is the strain rate. And the way you can look at this equation is basically you take these first two terms. That would be the along streak direction. The second moment, as a function of time, grows proportional to the strain rate, such that the solution here is an exponential stretching of the tracer patch. Meanwhile, in the cross streak direction, so let me describe that here. Okay, so here's the along streak variance. Blue dots are our estimate of the length of the patch. Again, these latter ones, we didn't sample the whole patch, so those underestimate. But what we see is on a log linear scale, time here, logarithmic here, a straight line is an exponential stretching. So early on, we saw a stretching rate of 3 times 10 to the minus 5 inverse seconds, and then it slowed down in its stretching. It's still getting longer, but at a slower rate by the end, 5 times 10 to the minus 6. And again, those are fairly typical mesoscale strain rates. Okay, now in the cross streak direction, what's happening in the cross streak direction is this gamma is negative. It's converging in the cross streak direction while it's elongating in the along streak direction. It's like taffy, right? You pull it this way, it gets thinner that way. But diffusion stops it from getting infinitesimally thin, because as you increase the gradients, diffusion has a bigger effect. It's the diffusivity times the gradient that is what matters for the flux. And so you can imagine then that the convergent strain and the divergent tendency of the diffusivity could balance to get you a steady state width. And in fact, that's what we saw, is that once that patch started elongating, it stopped getting thinner, and it pretty much stayed the same width, even though it kept elongating. And so as a first approximation, you can say, okay, d sigma squared dt is constant or zero. There's no rate of change of sigma in the cross streak direction. And so then you cross this off, and you can estimate the diffusivity from knowledge of the strain and knowing that the strain and the diffusivity are competing to set a constant sigma. So if you take these strain rates from the along streak estimate, assume that it's horizontally non-divergent, that is, any elongation is countered by a convergent strain, then you can take your second moment in the cross streak direction, the blue dots, and take your pick of the strains. The first 3 points, if I were to fit this strain rate, I would estimate a diffusivity about 1 meter squared per second in order to maintain that streak width. If I had a higher strain rate, a lower strain rate, shallower slope, later in the experiment, I would estimate anywhere from 0.6 or 7 meters squared per second up to as high as 4 meters squared per second. So those are my estimates of the horizontal diffusivity in the presence of a strain field. So that's how we use our bulk dye studies to get the statistical number. What is the number that is the diffusivity, right? That's the first order question. Now, the more interesting question in some regard is, okay, what's causing this? What's driving this diffusivity? And that's what we're trying to get into the detail of. Okay, this is strain estimated from drifters. Sorry, I forgot to mention this. The strain rate, we had drifters in with our die. As we deploy the die, the drifters, GPS drifters help us track the die. And this is just sort of an independent estimate of strain. The red line is the strain, the blue is relative vorticity, but the strain rate units here are 1 up to 3 times 10 to the minus 5 inverse seconds. So you see it starts out around 3 times 10 to the minus 5, which is about what our fit was here for early on. And then it drops down around 1 times 10 to the minus 5, which is this reduced strain later. So it's consistent with an independent measurement. Okay, so one question is shear dispersion. That's sort of the canonical mechanism. Well, from these die data, we have everything we need to estimate. Can shear dispersion do it? We have ADCP data everywhere that, anytime the ship is sampling the die, which was just about the whole time, we have the velocity profile under the ship, so we know the shear. From the die, we can diagnose exactly the diapycnal diffusivity, and so the diffusivity combined with the shear, we can put together a model that has, die concentration, rate of change of concentration. W here is the three-dimensional strain tensor. We're accounting only for horizontal strains, U and V components. Can be divergence, can be shear. And then we have a diffusion tensor that has just the diagonal terms. So these are horizontal diffusivities in the X and Y direction, and this is a vertical. So what we do is basically you imagine a Gaussian die patch and you have three-dimensional tilting and stretching of it, and we can do a model fit to this is the point. And so our model fit, the red points are the data from the observations, and what we basically do is we take that three-dimensional model and we say, okay, let's assume we know the shear from the ADCP, and we know the strain based on the drifters. What diffusivity would get us the answer to explain all the tilts of the die that we observe? And basically what we find is we need a diffusivity of order 1 meter square per second, 0.89, here. We also relax the model and say, well, let's actually also apply a scale factor. If we multiply the shear by something, allow the shear to be proportionally bigger than what we measure, because we don't resolve down to meter scales. We don't resolve the highest shears. Or the strain, if we under or overestimated the strain. Well, those scale factors end up being close to 1. So we're not grossly overestimating or underestimating for consistency with the data. But the important point is here, we can run this model and we can say, well, what happens, how well can we match the data if we just turn off the vertical diffusivity? And the answer is, we can still match it pretty well, but we still need that horizontal diffusivity. The vertical diffusivity, as plays a role in shear dispersion, can only account for about 0.1 meter square per second, not 1 meter square per second. So we have a pretty strong case based on our observations that shear dispersion can't explain what we're seeing. Now there's some caveats to that we're looking into about the episodic nature of mixing, but the first order answer is we still think there's some other process beside canonical shear dispersion. Okay, so this is the second experiment, basically the same result, different stretching rates. So let's get into the Lidar work. So in order to really understand the details, when you look at those ship surveys, and we're covering tens of kilometers with the ship surveys, we're going 5 knots with the ship. We get a profile about every 100 to 150 meters. So that's the resolution we're able to do. And it takes us close to a day to do a complete survey. And so we're not getting 100-meter resolution, right? That's the sampling, which means our Nyquist is 200 meters. So 100 meters and less, we're not resolving with the shipboard surveys. And so we've been looking for a way to resolve those smaller scales. The other thing is, if it takes us a day, we can't repeat sample something so that we see the evolution on hourly timescales or even minute timescales. So that's where airborne Lidar is coming. What this system is, we first started actually using a bathymetric Lidar. This Lidar is actually even more well suited to our die studies. What this is, for those of you not familiar with Lidar, this is an airborne instrument. This is a titanium sapphire laser, 480 nanometers, which is a blue laser. The blue is very well tuned for seawater attenuation, so it gets some of the best penetration we're able to get with Lidar. It has a 1,000 hertz pulse rate. So it's pulsing at 1,000 hertz. The pulse starts out 30 nanoseconds, is chopped to 10 nanoseconds, which ends up getting about a meter resolution in the water column when we do our inversion. So now imagine, and then it's scanning transverse to the direction of flight. It's doing actually a conical scan at about 100 hertz, a little under 100 hertz. I'm sorry, 10 hertz. And so we have, basically, as you're flying along in the aircraft, you're sweeping this around, and you're illuminating about a 100-meter wide swath at the sea surface with your Lidar pulses. Each pulse, you range gate the backscatter, and we actually also have a fluorescence channel on this. You range gate the return, and hence the range gating is why it's called Lidar. After, radar is radio detection and ranging, Lidar, light detection and ranging. So it's digitized the return at about 10 centimeter resolution. So we oversample the return. And then we do an optical inversion to get the attenuation and the backscatter and also the fluoresced light back. So what we're doing is we're using this laser as a fluorometer. The 480 excites fluorescein dye to fluoresce the emitted wavelength. For fluorescein is, 520 nanometers. It's a slightly different wavelength. And then we have a very narrow band filter. I don't have the filter information. Very narrow band pass filter for the fluoresced wavelength. That's our second channel. So we're looking at backscatter and we're looking at fluorescence. When there's no dye in the water, that laser pulse doesn't fluoresce off anything. We get noise floor in our fluorescence channel. When we hit dye, we see enhanced attenuation of the laser light because our dye is absorbing more laser light than seawater does. And then we see a bright spot in our fluorescence channel. And so basically what we do, and those of you interested in the math, I won't go into a whole lot of detail, but give you the essence of it. You have a downward propagating, first of all, you have a Gaussian laser pulse. So here's the laser pulse form. You have your energy, and it's Gaussian in time, which gives you a Gaussian length, basically translation. And then you take this and you put that in an attenuation equation. Here the attenuation coefficient is attenuation due to seawater and the dye. So anything that scatters or absorbs, it takes light out of your laser wavelength and doesn't send it back to you. That's what the attenuation is. And so your attenuation now, if you think about this attenuation, as I said, that's up in the exponent. Part of that is dye, is due to dye absorbing the light. So in principle, you can take your backscatter, and if you compare it to an ambient profile, the enhanced attenuation is attributable to dye loss to absorption and re-emitted at a different wavelength, which doesn't come back in your laser channel. Meanwhile, your fluorescence channel gets more complicated. Now you have an attenuation coefficient that's not just at the laser wavelength, but basically you have your blue light coming down, absorbed, re-emitted as green light, and that green light is attenuated on its way back up to your receiver. And so now this attenuation coefficient has both your laser and your fluorescent light in it. And how much light you get back is proportional to the dye concentration along with the dye attenuation coefficient. So this becomes now an inversion you have to do if you know the optical characteristics of your Lidar and your water, if you can estimate them independently, say from optical measurements in situ, then you can do an inversion to calculate absolute dye concentration. So here's what we did. This shows the final survey of that first experiment. You can see the black ship track and the red dots. Okay. Green here is a little satellite fluorescein experiment that we did next to our main rhodamine patch. And blue is where the Lidar surveyed. So this is a 100-meter wide swath illuminated by Lidar. So this shows the aircraft tracks back and forth, surveying our dye patch. Okay. So what we've done is we have this coincident with our big, longer, 6-day patch that we can estimate the statistical quantity of diffusivity. We have a small patch that we only followed for 6 to 12 hours that we can look in a lot of detail on. So now I'm going to zoom in on this green patch. And so here's just for context that previous picture, but here's one set of these blue swaths illuminated by the LiDAR going over our fluorescein patch. So the green here is the injection line. That's along the ship track while we're pumping dye. Black ship track, here we're pumping dye as we go along, stop pumping, and then we come back and we're doing some surveys. Meanwhile, the aircraft did these 3 passes over it. And on those 3 passes, it saw dye here, here, and here. All right? And then we just repeat those overpasses. Now we're doing this, it's at night, we're out in the open ocean, 200 kilometers from shore, trying to coordinate with the aircraft. And so, and we're trying not to lose the dye ourselves. So we're trying to direct the aircraft. Again, to give you a sense of where it is, this is down at about 27 meters, 28 meters. These are velocities. So you see here it's going about 20 centimeters a second, not much in the east-west direction, but it's going a little bit southward, I guess. Negative. Yeah, so southward. And so now if you now take the repeat overflights of that, so the upper panel here, time is up here after release. For reference, this is the scale for our injection. This is 1 kilometer. And I have a blue background here, but the blue splotches in here are in between the passes of the LiDAR that you see pick up the dye. So here's the first set of passes. Here's the next set of passes after 3.7 hours. Here's the next set after 4.4, 5.3, and 6.3. Now, I showed you the equations for what we need to do for the inversion, but for simplicity, what I'm showing here is the peak intensity of the return. This is roughly, remember I said there's a coefficient out front proportional to dye. At a fixed depth, this is roughly proportional to dye. So I'm just showing peak return in this upper panel. And then this lower panel, I'm showing the depth of the peak return. And so here's a scale here from 30 to about 42 meters. And combine these 2 pieces of information tell us a lot. First of all, our dye patch has gone from its 1 kilometer and it's elongated. Now what I think is the case is this right here, I think is our original dye patch, this initial streak. And I think what happened was there was a plume of dye that got swept up during the injection or shortly after into shallower, lighter water, deeper water, right? This dye, if you look at the depth of peak return, this is deeper than the southern. The northern part is deeper than the southern part. In all of these images, reds, yellows here, reds, yellows here, yellows, blues here, yellow and red. So this dye is shallower than that, and the dye appears to have been sheared off northward based on the across isopycnals. Another interesting thing you can see is in some of these later ones, you can see there's a preferred orientation. There's some banding here. We're not really sure what that is. What's interesting is that banding is actually perpendicular to banding that you see in the depth of the peak return. And so this, we think, has to do with undulations by internal waves, but then there's something else happening here. And the question is there some sort of shear or roll instability happening with these internal waves that are creating rolls in the opposite direction? So that's a hypothesis we still need to investigate. But one of the key things is you see that within a half hour, successive surveys are capturing most of that patch. And this is a kilometer scale patch. And that's something the ship can't do. So I'll go to the next one. We did 4 of these satellite releases. I'll go to the next one. I'm sorry, here, 4 in the next one. Just to give you a sense of, remind you, this is, we're taking each LiDAR pulse and we have the depth information. So this is, if you take a transect across this, a synthetic transect through the data, this is the LiDAR data. Here's the intensity as a function of depth and distance along a transect through the patch. And so you can see we're able to isolate the dye in the water column as well, not just laterally. So we really do have the 3-dimensional information about the dye patches. And you can see these undulations, right? Here are these undulations that show up in the depth of the peak return here. So here's the next one. This was done just a little bit to the east of the second release that was straining in the north-south direction. And so again, we have the zoom in here. Here's the injection line, the green line here. And then the first LiDAR survey, you see we covered it pretty well. These were north-south transects for this one. give you a sense of the velocity here. Again, this is at the depth of the die. It ends up being about a knot northwestward current that the whole thing is moving, and hence this gives you an appreciation for trying to have the aircraft follow this without real-time information from the aircraft. We don't know what they're seeing until they land and send us the data. So we didn't have that going yet, but that's something we definitely want in the future. And then the green dots here are some of the hits from the ship that we really did find die where the aircraft was saying it was die at about the coincident time. So we're matching those up. So let's go to the survey. So we had fewer but more complete surveys for this release. This is after about 3.5 hours. Again, here's a scale for 1 kilometer. And you see this is a crazy looking patch, but let me explain what's going on. So here, again, the injection streak, if I go back one, the injection streak was roughly oriented in the direction that survey did show, right? The injection streak was about like this. So I think this is the main axis of the patch. Now all this stuff, these finger structures off to the west, notice if you look at the depth of the peak return, these are all shallower than the main part of the patch. So again, it looks like there was some die that was a little bit shallower, and if you look at the velocity data, you can also see that there was a shear, and so that shallower die is getting sheared off to the west. And while it's getting sheared off, there's something about it that's causing these filaments. Now, what we think that is actually an artifact of our injection. And that is, if you imagine that we're towing our sled along and we're trying to follow an isopycnal, we never do that perfectly. There's always some standard deviation following the isopycnal. So you can imagine we're injecting, cutting through internal waves. So on average, this die is going to be heavier than this die. It's going to be on a heavier isopycnal. And so when those waves are bouncing around, because you're injecting it very quickly, you're cutting through, the die that's on shallower isopycnals will now get sheared off if there's a shear. And so we think that basically every time what this looks like is, on average, now your die looks like this, and now if you shear that, you're going to get something that looks like this. So we think that's what this is that there was die shallower that cut through isopycnals, and then that got advected off. But we can actually do something with that. We can look at that and say, okay, well, this is 3.5 hours after injection. This is almost 5 hours after injection. If these originated from the injection, they've persisted for 5 hours. The scale of these is only about 40 meters. In order for a feature like that to persist for 5 hours, the horizontal diffusivity must have been less than 0.1 meters squared per second. It can't have been more, otherwise it would have smeared these out and you wouldn't see the individual filaments. Well, that gives us a different estimate of diffusivity. It couldn't have been bigger than 0.1. But my large-scale experiments, I estimate it's of order 1. So what's going on there? Either different processes for different times or scale-dependent diffusion. I'm inclined to think scale-dependent diffusion, and the question is, what's that transition of scales that's happening? But this is a pretty strong case, I think, that it can't be on this scale. Now remember, this is only 5 hours, and the later experiments were 6 days long. A lot can happen with inertial oscillations, with instabilities over 6 days that you wouldn't see in less than half an inertial period. All right, so there's potentially different processes at work here, and that's what we're trying to get at. Now another thing you can do with this is, if you look at this first survey and then the next one, you can get a sense this is a little bit bigger scale now. It's grown a little bit in the 1 1/3 hours that's elapsed. And if you look at some of the features, you can see, for example, this feature is new. That didn't exist here. These two features, there's sort of a 2 fingers sticking out here, those have spread. There's this bolus up here. This is not an artifact of the conical scanning. This is a real die radius of curvature. And you can see how these finger-like structures are wrapped around here. That suggests that there's an eddy or something there, small-scale curvature to the flow that causes this to wrap around. And so you can start to look around at different features. The tip of this one is the tip of that one. The tip of that one is the tip of this one. You can identify different points to the point where you can actually say, if I difference these two images, what velocity do I come up with? And so that's what we did here. And so this is just really still a crude cut at this. And I know the satellite remote sensing people have developed much more sophisticated algorithms for this, but I'm catching up. What you get is basically you see the flow field that you get has curvature down here where these fingers are developing. It has curvature up here. The velocity is opposite direction here than here. Now, remember I said I think there's a shear that's doing this, right? So a lot of these arrows have to do with the shear, that this die is moving this way because it's higher in the water column relative to this die. Okay, let's subtract that out because I have the depth of return for each of these LiDAR points. So now I can subtract out the mean shear. If I subtract out the mean shear, here's my residual after I remove that shear. And now you can really see the curvature of some of these things and the differential velocity. And that's what we're after. What is the small scale velocity that's stirring our tracer? And hence, what are the processes driving that? Now, I'll go to the last experiment with it's a different dynamical regime, but I find it fascinating as well, dynamically as well as just highlighting what this approach can do using the LiDAR. This is a place where the time scales are even shorter. This is a mixed layer experiment. What we did was a combined experiment. We did our dye injection up here. This is down here, just again a little bit to the west of the main patch that we were following. We injected down at 28 meters or 27 meters. Then we brought the sled up to 3.5 meters and injected another 5 minutes. So we did a dual deep and surface release. And what happened was very quickly those two separated. This is the deeper release, this is the deeper injection. And then the surface patch got advected roughly downwind, away from that surface patch, as you would expect. There's a shear across the base of the mixed layer. And so this is what that surface patch did. So here it is after just 15 minutes. There's our bit of surface, and there's the little tail that had connected it to the deeper piece. And after just a couple of hours, you see it has developed into these features that have tails streaming off. Now, this was all injected at 3.5 meters, but these tails are plumes going down into the mixed layer, and hence are being sheared off and left behind by the dynamics. And then you see that associated with that also, our straight line injection has evolved into these boluses. So this is consistent with large eddy circulation in the mixed layer. There's now in this case, coincidentally it's downwind, but we don't think it's associated with actually wind Langmuir circulation. And the reason is, so if we look at some cross sections through one of these, and I'll look at this one in particular, you can see that these tails are going down from near surface down to 15, 20 meters. That's the base of the mixed layer, we know from our ship-based surveys. And at the base of the mixed layer, they're being left behind, they're tailing behind. Eric Skillingstad at Oregon State University did some numerical simulations. Langmuir circulations, put the wind on there, he gets some large eddy circulations, but they're not quite like what we're seeing. If he turns off Stokes drift and he puts in his model a baroclinic front in the mixed layer, like what we had here, he gets large eddy circulations that mix this fluid down, and in fact, with a front, you have a horizontal density gradient in the surface mixed layer. And so isopycnal mixing can be vertical mixing, but then when it gets to the base of the mixed layer, it becomes horizontal, because by definition of the base of the mixed layer, isopycnals become flat. And what we were seeing from the in situ measurements is that our dye was making it into the stratified water at the base of the mixed layer. And so his model confirms that what's happening is there's the geostrophic pressure gradient and shear that's happening from this front, and what's happening is we're getting isopycnal mixing down isopycnals into the base of the mixed layer. It's not detraining, it's not making it part of the mixed layer, but it's actually a process that's subducting water down into the stratified water. But again, the point is the the three-dimensional resolution shows us the large eddy circulation as well as the tails, plus a few ancillary measurements confirm that it's getting into the stratified water below. So that's basically, what we're doing with LIDAR. And the key thing here is that these large eddy circulations, you see, they're starting to develop within an hour. It's tens of minutes time scale. Without a complete survey of the patch, you wouldn't have nearly as good an idea of what's happening dynamically. So to summarize this science part, we had our dye release experiments, basically our large-scale experiments where we estimated the diapycnal and horizontal diffusivities and also the strain rates from that. We get values anywhere from a half up to about 4 meters squared per second. Consistent remarkably between the two experiments, the horizontal diffusivity, despite the much different strain rates, almost an order of magnitude difference in the strain rates. Our best estimate right now from internal wave shear dispersion and even mean shear dispersion, right, based on our ADCP measurements, is that shear dispersion can't explain what we're observing. Our LIDAR mapping suggests there is some small scale stirring that's happening based on those velocity measurements, right? You can see the curvature of the patch. You can see there is small scale advection, differential advection happening. And at those scales, we estimate an upper bound on the diffusivity that's an order of magnitude smaller than these values, so 0.1 meters squared per second. So it's just the process of teasing apart, and there's a whole slew of other observations that happen as part of this experiment that we're still working on the data to try and piece all the pieces together. And I'll just do a plug for a future seminar. This LatMix experiment was a two-phase thing. We also went out in winter of 2012 and we did dye releases at the north wall of the Gulf Stream to look at very strong frontal conditions and very strong wind conditions, and we got some amazing results there that I'll talk about another time perhaps. Okay, so that was the science part. Now I just want to tell you what we're up to a little bit at UMass Dartmouth, in particular relative to our new Experimental Center for Environmental LIDAR. And the players are listed here. Myself and Brian Howes at UMass Dartmouth, and then we have collaborators on the other UMass campuses, Supriya Chakrabarty, Tim Cook, and Dave Willis at UMass Lowell. Their expertise is in, Supriya and Tim Cook do terrestrial LIDAR. Tim is an engineer and has built LIDARs for terrestrial applications, forestry. Dave Willis is actually a mechanical engineer, but he's interested in wind turbines and understanding the dynamics around wind. Also involved in wind LIDAR is Matthew Lackner at UMass Amherst. They have a wind LIDAR and interested in wind farm applications, basically resource assessment and wind turbine wakes. It's remarkable what wind turbine wakes can do. And Crystal Schaff at UMass Boston. And so just to give you a sense, we have these three thrust areas. We have terrestrial LIDAR. This is the Lowell and Boston work. Here's an example of their Dwell LIDAR for forestry applications. It's a dual wavelength laser, and basically what they're doing is they're using the two wavelengths on a tripod mountable, so this can go on a backpack and go into backcountry forest. And it's ground truthing for forestry measurements and biomass estimates. So they have the two wavelengths. One wavelength is very good at picking up foliage that, anything that's opaque, they'll get a return from their LIDAR. But one is more sensitive to water in its return, and one is not, and therefore you can differentiate the opacity of your canopy, what is leaves and what is trunk. And the trunk is what makes up the biomass. And so that's where it's important for, by the time you relate the in situ measurements to remote sensing measurements that are, going over rainforest, that biomass estimate is the critical piece of it. The second area of application, which is what I was just talking about, is oceanographic LIDAR. So we're going from terrestrial, trying to cross that air-sea interface and do applications for the ocean. What I talked about was the airborne LIDAR for the dye studies, like down in this lower right-hand corner. But actually the first system that we used as a proof of concept, so our contribution to this over what bathymetric LIDAR people have done is we're the first that did the three-dimensional inversion for dye concentration in the water column. Other people have used the vertical information, but I think it's underutilized, and that's something I'd like to build on. But basically the bottom line is it's what's referred to as a full waveform LiDAR, that you get the sea surface, you get the bottom, you get everything in between. And we're using that for dye, but there's a lot of other applications across the air-sea interface in coastal areas and topographic mapping and bathymetric mapping. And then the last area is wind LiDAR. That's, again, I said one of the Lowell folks and the UMass Amherst. And that's relevant down in our region in particular. We have a couple of offshore renewable energy projects going on. There's the Cape Wind project, which is wind turbines. Now, I found this is an interesting picture from off the coast of Denmark, right? A fog bank and how it shows up in wind turbines. This is what LiDAR can do for a wind turbine field. What that is the momentum deficit associated with wind turbines. And you can see the wake, the momentum deficit in the wake of a wind turbine. And that has very important consequences to a downstream turbine that's getting hit with turbulence. The stresses on the blades are intense. And so it's a mechanical wear on the turbine as well as an efficiency problem. And then, of course, you put anything in the water and you have the potential for scouring and burial, and that's where that crossing the air-sea interface would be very useful. When you put, whether it's a wind tower or a hydrokinetic device in the water, you have applications. And so there's another testbed project in Muskegon Channel for a hydrokinetic device, underwater device. And then, of course, LiDAR has the potential of measuring surface waves, and that's relevant to a wave energy project. And so that's basically the areas of application. This development of a center, we're at different stages of maturity of the different aspects. The terrestrial LiDAR and the wind LiDAR are probably the most advanced in the UMass system. I'm pushing for the oceanographic LiDAR, where I have some experience now behind me, but we're trying to develop this into something bigger, and hence coming here to basically talk about potential collaborations and talking to anybody who has shared interests or applications related to any of these areas about the terrestrial or oceanographic or wind LiDAR. So I'll stop there and I will take questions. Yeah.
So Miles, from an operational perspective, first of all, how do you release the dye? Just throw it from the aeroplane, or do you put it in a pipe?
No, what we've been doing is the in-situ release, where we have a towed body behind the ship, and we pump it down a water hose that's zip tied to our CTD, basically. And we have a little injector, it's like a sprinkler head, basically. But it's very important for us to know where it is in density space. And as you see, the LiDAR really showed us what can happen when we have even the minimal error we have. I mean, our RMS standard deviation in the water column, when we're tracking an isopycnal to inject, is typically a meter or at most 2 meters. We're actually able to follow pretty well, even though isopycnals sometimes are heaving 5 meters. But even that little bit of error, you can see, can have a significant effect. I would love to release it from an airplane. I've released XBTs, AXBTs and such, and there's no reason you can't do that from an airplane as well with dye. And you could do surface mixed layer experiments and turn around and do your overflights from minute 1, basically.
How long does it take to do a survey from a large scale, that like after 4 hours, 6 hours, but the dye is in the water? How long does it take to do a LiDAR survey?
Well, so the surveys, so you have about 100-meter swath. And what takes the most time, if you have a kilometer, let's say a kilometer patch of dye, it takes about 20 seconds to fly over it, and then about 4 minutes to turn and come back and do your repeat flight. So in order to march along, it takes about an hour to map about a kilometer squared. If you were able to do it with a helicopter or a blimp or a more stationary platform, you could do a survey quicker than that. But really, it's as much limited by the turning time as anything. But it's about an hour. Now, if you have 5 kilometers long and just a kilometer wide, it's still about an hour, because it's another 20 seconds or another minute. It doesn't that's still small compared to your turning time. So it's all about strategizing how you're going to do your survey as much as anything.
Could you do this with an AUV?
Sure. Now, what's the question you want to ask with the AUV? So, I mean, there are compact LiDARs, and I think, well, Shahak, you would know about who's mounted them on AUVs. But there are compact systems. One of the things I like about the airborne is the rapidity and the scale of the surveys. If you put yourself in situ, you're already going slower automatically. The advantage is
You can follow the same.
you can go deeper.
Yeah, you can
Right.
follow the whole thing, just let it, track it.
Yes, you could. Well, but what's the advantage of an AUV mounted LiDAR over an AUV mounted
Cheaper.
fluorometer?
Oh, no, yeah,
Right.
it's the AUV is cheaper than.
Yes, yeah.
airplanes.
I mean, we've had as part of this, actually, there were some autonomous vehicles, gliders, as well as a Remus AUV that surveyed the dye patch as well. They had fluorometers mounted. So yeah, that's doable.
But the disadvantage is that you're seeing a smaller swath of an AUV compared to an aircraft, you have a wider swath.
Right. Yeah, so again, it depends on the physics you're looking at, which is why I say, what is a particular problem you're interested in. There would be times when you would want an underwater one.
You mentioned on one of your slides you had what looked like wind speeds and directions.
Yep.
Did you have to model that to determine what the attenuation would be owing to any braking conditions that might have gone on during your experiments or any surface?
No, we had pretty minimal, the winds I think got up to 10 or 15 knots. We weren't getting a whole lot of white capping most of the time. The losses at the air-sea interface are one piece of the problem that I think as much a challenge as any, and I think you can basically account for those. If you can constrain how big they are, the difficulty of the inversion is that exponential profile once you're in the water column, because it's a very unstable inversion, basically. But think of it as the LiDAR measurement. Once you're in the water column, you're measuring attenuation, and it's a difference calculation, rate of loss of light or rate of emission. So bottom line is we didn't have enough problems that we felt we had to worry about it. Now, in more white capping situations, I'm sure it would come into play, but I don't have familiarity with that problem. Yeah.
In your equation where you had two attenuation coefficients, one for the diffuse attenuation of light and one for the fluorescence.
Yeah.
How did you calculate those two attenuations?
Well, we have we can estimate the LiDAR attenuation coefficient based from its own measurements in ambient water. We also had the Satlantic inherent and apparent optical properties measurements, so we do have an in-situ constraint on those. But basically, it comes down to we're making some very just blanket assumptions about we have a LiDAR attenuation coefficient. We know the characteristics of the LiDAR, where we are in the beam versus diffusive limits, and then we know what type water we're in, Gerloff water type 1, and so then we say, okay, if we know it at roughly at 480 based on the system parameters, we can make a guess at what it would be at 520, and we go from there, basically.
You do a Gordon correction to calculate at the fluorescence wavelength.
Yeah. So we assume a different attenuation at the fluorescence wavelength, but based on published literature, not detailed observations. Jeff?
Were you surprised to find internal waves out in the middle of the gyre like that?
No, we were expecting internal.
I think
the
it'd be
Garrett and
more on
Monk
the
spectrum
margins.
says they're everywhere, right?
Well, yeah,
And
but
so-
I would think that'd be much more prevalent on the margins, in the periphery of
Well,
it.
tidal internal waves, but there's a broad spectrum, and yeah, we still do see tidal and inertial peaks. But there's a lot of inertially, generated motion out there as well. Yeah.
So I'd like to explore the nature of sort of having LiDAR as the organizing component of your new program here, as opposed to a particular line of inquiry. Do you anticipate sort of multiple kinds of data sets out of the same LiDAR system, or what's the synergy that you see other than sort of the engineers that are tinkering with the LiDAR?
Well, I think there's a lot of, so from my perspective, I'm a physical oceanographer. I'm a user of LiDAR. I don't design them, and I have collaborators that I've been lucky enough to work with. But the difficulty from my perspective is, as being a single PI at a state institution, having basically my pet project warrant purchasing $1 million system, and the maintenance and the engineering and the basically the cost center associated with that. That's one of the things we rallied around to team up. And so the similarities, there are a number of similarities between the terrestrial and the wind and the oceanographic LiDAR in terms of the hardware and the engineering expertise, in terms of the data algorithms and inversions. So there is that side of it that I think is credible as a region to rally around. In addition, the renewable energy, I think, is a study topic that there are many applications you can imagine, and also basically coastal ecosystems is another area that we're trying to rally around, and being able to go from basically the terrestrial, the land, through to underwater seamlessly, so that you can study marshes. You can study the LiDAR with the terrestrial systems. They can map a marsh and differentiate between Phragmites and Spartina altiflora, the different types of marsh grasses that grow on different parts of the marsh plain. And if you can then go smoothly into the water column to get the bathymetry and start to look at basically whether it's sediment transport processes or tidal flushing, erosion on the banks of a marsh channel, that kind of thing, all the way out into deeper channels and dredging related issues. So it's just a matter of these are problems that, as a New England state, we're all interested in, and there are important consequences to understanding that boundary. And so that's another area we're trying to rally around, basically.
All right, if there's no more questions, we'll give them another round of applause.